Okay, uh, this is my thesis defense. My name is Bing Wang. This thesis is developed uh, in the doctoral program that named Automatic Control Robotics and Computer Vision. So the title of this thesis is Modeling and Vibration Control for Submerged Piezoelectric Cantilever Beam. uh, and the science is supervised by Dr. Roman and Professor Jing Na. So I'm going to introduce this from the following 5 aspects. The first part will be the introduction, and the second part is the modeling of the beam system. Then I will talk about the parameter estimation and the vibration control. Finally, I will give some conclusions and future work. So let's move to the first part, introduction. As you may know, for renewable energy, water power using water turbines has become an essential part of our electrical power supply. A salient advantage of the water turbine system is it can shut down and powering up again very quickly by changing the wicket gate. That means the working load are changing. So it can enables better use of wind energy and solar energy that depends on the weather. As you can see in this figure, it is a basic structure of the water turbine. You can see at the top is a generator, including the stator and the rotor, and with the shaft, they're connected with the turbine in the bottom. So when the water flow into the turbine, the blades will be rotate. So the main problem in this rotating blades has vibrations. So the vibrations induced by the vortex braking are different with various flow loads. The vibrations can lead to damage to the runner blades and the shaft, which will be deteriorate the performance of the power output. This is a basic profile of the vortex rope. So at the top is turbine blades, and in the draft tube, it will induce the vortex rope when the turbine rotates. So the vortex will induce a lot of vibrations that can damage the device. So that's what we don't want to see. To improve the efficiency and performance of the hydraulic turbines, it is very important to develop an active flow control system to ensure the turbine works safely in various operating conditions. So this is the main purpose of the European Union funded AFC for Hydro project. We UPC mainly focus on the fluid structure interaction problem. So for the purpose of focusing on the vibration of the structure of the water turbine system, we assume the blade of the wheel can be partly described by a flexible cantilever beam. So the problem is transformed to the beam fluid interaction problem, and the main goal becomes vibration suppression of the beam in fluid. In this photo, we can see the beam is placed in a cubic tank. Around the beam, there are different kinds of fluids. So the fluids make the beam vibration. What we want to do is to use actuators and sensors uh, to suppress the vibration. The experiment test bench is this one. So we have a cantilever beam uh, vertically placed in the cubic tank. So why we put it vertically? That's because in this manner, we don't need to consider the gravity force, which is more convenient for us to study. So in the cantilever beam, we have the piezoelectric actuator and string gauge attached, and in addition, we have a device that called the compact reel. So this is a real-time controller, and we have the stream measurement module to collect the data from the string gauge, and we have a signal generation module to generate the control signals, and a signal monitor module to know how much voltage we applied on the piezo. And we have an amplifier that allows us to guide enough voltage that can suppress the vibration or excite the vibration. This is the structure of the experiment setup. So on the left, we have the cantilever beam system, and we use string gauge, stream measurement module to collect the data. And the data can be collected with the compact reel. In compact reel, we have downloaded the program from the computer, so the program can run on the compact reel in real time. As a computer, we can see the figures that plotted the information we collected. So with the compact reel, we can generate the signals that we want because we have programs inside it. With a signal generation module and the amplifier, we can generate the voltage to the piezoelectric actuator, and then we can use the piezo patch to suppress the vibration. So the thesis objectives can be summarized as follows. First is to develop control-oriented models. And the second one is to investigate the parameter estimation methods to online estimate the unknown parameters of the beam system. A third one will be the design control algorithm together with the unknown dynamics estimation methods to suppress vibration. And finally, we will study the applicability of the design control framework with simulations and experiments. So let's go to the modeling of the beam system. From this figure, we can see the cantilever beam model, the basic structure of the piezoelectric actuator and the string gauge. This is the same as we have in the experiments. So, so the beam can be excited, or the vibration or can be surprised by using the piezoelectric actuator. And the strain gauge works as a sensor to measure the strength of the vibration. So to model of this beam, we computed the kinetic energy and the potential energy and the works done by the piezoelectric force, or no, by the damping force and the piezoelectric force. So how can we compute the piezoelectric force? We can have the control moment of the piezoelectric actuator, and then the voltage applied on the piezo patch can be represented by using two heaviside step functions. So then we can compute the piezoelectric force. With this force, we can use Hamilton's principle and the following and develop the cantilever beam model. Hamilton's principle is it means the motion of a dynamic system in a given time interval is to maximize or minimize the action integral. In practice, almost all the cases are to minimize the action. So for deformable bodies, the Hamilton's principle can be given by this equation. We use this Hamilton's principle, we develop the beam model. After we had the beam model, we investigated the fluid dynamics. Ideally, the fluid dynamics should be described by the Navier-Stokes equation and the continuity equation. The continuity equation means the divergence of the velocity field is zero everywhere. Directly implement Navier-Stokes equation is difficult because there is no pressure and velocity relationship in the continuity equation. So we derived the Navier-Stokes equation and the pressure Poisson equation. So we have three equations and three variables, Vy, Vz, and the pressure P. Theoretically, we can solve the equation by using numerical iterations. However, there are some problems. We can see first the results we had. This is a fluid domain at the left wall and the right wall and the bottom wall. It is fixed with walls. At the top, it's a free face open area. So at each point, we computed the at both the spatial and the time point, we have computed the pressure at each point in the fluid domain. So theoretically, we can place the beam inside the water and where we want, and then compute the fluid interaction force. So we can have the PDE-based models using Navier-Stokes equations and the beam model, like in this form. However, there is no analytical solution solving this equation. So numerically, solving it is should be acceptable if the process is well enough. However, we cannot we are not able to implement it with real-time interaction. So we decided to simplify the Navier-Stokes equation to simplify the fluid dynamics to the different kind of fluid forces. We describe the fluid forces finally with the added inertial force and the squeeze flow force. So the dry beam model can be then transformed to the submerged beam model with the fluid forces. This is a Euro case for the submerged beam model to study the dynamics and the behaviors in practice. So compared to the existing models, the derived PDE model included the Kelvin-Voigt damping and the piezoelectric effect and the fluid force. So it can better describe the submerged beams characteristics in practice. Although we have developed the PDE-based models, we have certain problems in implement the PDE-based models. The first is it is difficult to solve because there is no analytical solutions. So we have to numerically implement it by using the discrete methods. In the numerical implementations, it can cause another problem. It is time-consuming to implement. Sometimes it cannot be achieved for real-time implementation. To solve this problem, we have many simplification methods in the literature. One of the methods is Galerkin's method. This method is straightforward and keeps the physical meanings of the states and the parameters. Another one is a balanced model order reduction method. This is also a mature approach that can reduce the model's order. However, this method cannot reserve the physical meanings and the states. So the states information are totally changed. Other methods like differential quadrature method, and also in the literature, many other methods. Finally, we chose to use the Galerkin's method to continue our research because this is more flexible for control design, and we can reserve the information of the original system. Although although we have developed the uh, reduced order model, we can have many informations that is the same like the original model. So we compared the forward model with the Galerkin's model. We first compared the first mode Galerkin model with the forward model. The forward model we chose is the 1000th order semi-discrete model. This model we implemented it with finite difference method. We can see by using the Galerkin's model, we can reserve the first vibration mode in the, we can see the first vibration mode is reserved and the other high or higher frequencies are ignored in this model. So the same is in the phase. We also compared the two models in time domain. So we released the beam model is released from 1 centimeter, and we see the behaviors. We can see the blue line is the forward model. It has a lot of harmonics, but the Galerkin's model have only one sinusoidal signal, like because it is reduced to second order model. So the other harmonics are ignored in this model. We also compared the forward model with the first two modes Galerkin model. We can see the two vibration modes are reserved as in the right line I described, and the other high frequencies are ignored. So with these two mode Galerkin model, we have compared the output of the in the time domain also. We can see the two harmonics can be described most of the dynamics of the beam system. We also compared higher order modes Galerkin model. Uh, the order increased while the performance doesn't increase significantly. So we finally chose two mode Galerkin model to conduct the parameter estimations and the analysis. In this part, we have some conclusions. A PD-based model is provided for the submerged beam, and second is the model is described by a semi-discrete model and a discrete model. To implement and analyze the proposed models, where finite difference method is adopted to discrete the beam model. Another conclusion is that ODE-based model is derived. Galerkin's method can retain the physical information of the space compared with the balanced order model reduction method. So it is more flexible for parameter estimation and control. So let's move to the parameter estimation part. I have divided the parameter estimation into sections. One is for the first mode beam system. For this system, we can measure the states. So the methodology is given as follows. The state space formulation for the system is a second order system. So we can measure the states by using the 11th differentiator. After we had the states, we define a set of filtered variables, and a parameterized form can be obtained, where psi is a known regressor and theta is the unknown parameter vector that need to estimate it. Inspired by the work developed by Professor Jing Na, with we further tailored this method on the beam system. We define the auxiliary variables as uh, as in this form, so we can obtain a variable W that contains the parameter estimation error information. As you can see, the W is driven by the parameter estimation error. So the persistent excitation condition can be online validated by using this method. The persistent excitation condition is necessary for parameter estimation at the moment. So it is not so straightforward and easy to online validate if it is persistently excited. So, but with our method, we can validate by test the positive definiteness of the matrix M. The structure of the proposed parameter estimation is generalized in this. We have the beam system, and we can measure the information of the output. We use the Levens differentiator, and we can obtain the states of the system. And after a filter operation, we obtain the variable W that contains the parameter estimation error. So we can design the adaptive law to estimate the unknown parameters. We have the simulation results here. This figure shows persistent excitation condition is fulfilled, testing the minimum the minimum eigenvalue of P. We can see all the values are positive, so it shows this is persistent excited. This is the results we had for states estimation. You can see the states can be estimated within a short time, and the parameters can convert to certain values. To show the effectiveness of the proposed method, we reconstructed the system output with the estimated parameters. We can see that these two outputs are consistent with each other. So here we have the experiments results for the driving, means the beam submerged, the beam placed in air without water surrounding. We can see the displacement and velocity can be obtained by using the observer. There are some noises in the velocity because the gene should be chosen larger in the Lagrange differentiator. So this is the parameter estimation results. We can see the parameters can converge. So with these two parameters, we reconstructed the system output. As we can see, this compared with the experiment output, the reconstructed model output can basically describe the profile of the system output. We then tested the submerged beam. We can see the states can be obtained by using Lagrange differentiator, and the parameters can be estimated. We reconstructed the system output. Although we can see there are slight discrepancies, but the basic profile are nearly had the same behavior. Here we have some conclusions. In this part, we mainly address the parameter estimation problem for the beam system with the first oscillation mode. The states of the system can be estimated by using Lagrange differentiator. As the parameter estimation error is extracted by using an auxiliary filter. A new adaptive updating law is derived based on the estimation error. By using the Lyapunov theory, the stability of the system is proved. Simulation results and experiment results show the effectiveness of the proposed estimation method. So for multiple mode beam system, it will be more complicated because we have a higher order system. The model can be described by the state space form. In here, we chose two vibration modes to illustrate our method. We can see the state in bar K1, K1 bar, K2 bar, C1 bar, C2 bar, and B1 bar, B2 bar as parameters that need to be estimated because they are related to the frequencies and dampings. We can express the system model as in the following ODE equation. To avoid using derivatives of the output y, because the output y can be measured, but the higher derivatives can amplify the noises. So to avoid this problem, we use a filter on both sides of the equation. Then we can obtain a parameterized form. So now the problem is to estimate the unknown parameter model parameters that based on the measured input u and output y. So in this method, we don't need to measure all the states, and the states cannot be measured. So to achieve this goal, we define the auxiliary regressor P and Q. Then the vector W can be formulated that contains the parameter estimation error. Then we develop a parameter updating law. Gamma is a learning gene, which is a positive constant, and H is a time varying gain, which is used to compensate the phi effect of the regressor. In this method, we can reconstruct the system parameters that in the state space model. You may know from the state space to the transfer function, it is easily, but from the transfer function to the state space, it can be complicated. So in this thesis, we proposed a method that is to determine the parameters in matrix A, that by computing the roots of the characteristic polynomial and the eigenvalues of A. So we can have four equations and four coefficients to compute. Another two parameters, B1 bar and B2 bar, we have the over constrained equation. So theoretically, we cannot solve it, but with more Penrose inverse, we can obtain the approximately solution of B1 bar and B2 bar. So the advantage of the proposed adaptive estimation method is the adaptive law is driven by the parameter estimation error. So the convergence of this algorithm can be rigorously proved. Another advantage is a time varying gain H is adopted to compensate the effect of a regressor. So the convergence can be enhanced. And the persistent excitation condition can be unvalidated by testing the positive definiteness of P. Here we have the simulation results. To fulfill the persistent excitation condition, we use the input signal, a square wave signal. So we can collect the output signal. And then we use the input signal and the output signal to estimate the parameters. We can see the parameters can be estimated. Of course, the parameters can be also estimated by using gradient method or least squares. Here we compared our method to the other two methods. From this figure, we can see the response. Both the transient response and the steady response are better than the other two methods. We compared the frequencies and damping ratios that use these three methods. We can see the adaptive method can achieve the best estimation. Similarly, we did the experiment in the test bench. So we input a square wave signal by using the piezo patch and collected the displacement using the sensor, using the strain gauge. So we have the parameter estimation results here. We can see the blue line is has a smoother response compared with the other two methods. To show the effectiveness of the proposed method, we reconstructed the model output. And the first is reconstructed by a gradient method, and the second least squares. The third one is constructed by using our method. We can see the performance of our method is the best compared with the other two methods. Within data experiment to compute the frequencies and damping ratios for the submerged beam in different level of water. So we can see the evolution of the frequencies and dampings. In air, the frequency is the largest. So I submerge the beam with different level of water. As the water increase, the frequency decrease. So for the frequency, for the dampings, it will be increased a lot for the submerged beam because the surrounding water work like big mass that attached on the beam, so the dampings will be increased. In this part, we have the following conclusions. A new adaptive parameter estimation scheme is developed for the submerged beam. Specifically, a parameterized system model is derived that allows online parameter estimation using only the input and output signal. A new parameter updating law is designed based on the estimation error. In this framework, frequencies and damping ratios of the beam system can be reconstructed. And the convergence of the parameter estimation error is proved by using Lyapunov theory. So the next part is the vibration control of the submerged beam. First, I introduce the unknown system dynamics estimator-based vibration control. The control objective is to surprise the vibration of the beam. So to achieve this, we define a set of filter variables by using a low-pass filter. So we can design the USDE by using the filtered variables. After we computed the unknown dynamics, we can compensate the unknown dynamics in the USDE-based controller in a feedback control. So to show the advantage of the proposed estimator, we compared the estimator with other estimators. One of the popular method is radial spaces function neural network. It can be used to estimate any unknown functions. So in this work, the unknown function is the unknown dynamics FW. So the FW can be estimated by using the neural network. Here, W is a neural network weight that can be online updated, and psi W is a regressor that constructed by cosine functions. Another method we compared is the extended state observer. The structure is it can be shown here. The ESO takes the lambda unknown dynamics as a new state variable. So a high-gain observer can be designed to estimate the states of the extended system. So we can see compared to the RBFNN, ESO and the proposed USDE have simpler structures. The equations are simpler than the neural network. And for the USD, another salient feature is only one designing parameters need to be adjusted. While for the ESO, there are three parameters, and the neural network, there will be more parameters. We compared the estimation performance with the proposed USDE neural network and the ESO. From these two figures, we can see the first line is with the proposed USDE. We can see the parameters can be the annual dynamics can be estimated accurately within a very short time. And the second line is with the neural network. I chose 5 neural nodes to estimate the unknown dynamics. So it is not so accurate. For sure, by increasing the neural nodes, it will be more accurate, but the complexity will be increased. The third line is the ESO. We can see the transient performance is poor for this observer. We conducted the experiments for the USD-based control compared with PD control. We can see in the left figure the PD control and in the right figure the proposed USD-based control. We can see both the controllers can surprise the vibration somehow, but the proposed USD have a better control performance because it can be used to stabilize the beam within 2 seconds, while the PD control uses around 5 seconds to surprise the vibration. For the submerged beam, we also tested the proposed controller. We can see the vibration is slightly surprised in this figure because the voltage that applied is saturated before the first second. So it means we have not enough piezo voltage that can surprise the vibration. But in around 1 second, we can see the vibration can be surprised because here we have the voltage, the displacement is smaller, so we have enough voltage. For sure, if we increase the range of the piezo force, piezo patch, we can get a better control performance. Theoretically, it is better to online estimate the parameters that to control this system because the system works at at different conditions like a system with other parameters. So, so that's why we design the adaptive control. To achieve the goal of vibration suppression, we define the auxiliary variable, including the control arrow x1 and its derivative x2. So then we can design the adaptive law, uh, control law by using the estimated parameters. These two parameters can be online estimated using the following auxiliary variable and the parameter updating law. The structure of the proposed adaptive control is given here. We have the beam system and we use a sensor to measure the states. So we can use a filter operation to obtain a variable m. And m is introduced to the parameter updating law that allows us to estimate the parameters using the estimation arrow. So after we had the parameters, we can use the adaptive controller to generate the control output. And then we use the actuator, the piezo patch, to suppress the vibration of the beam system. Here is the simulation results. We can see the parameters can be estimated within a very short time. And we compared this control with PD control also. We can see the red line is the proposed adaptive control. It can be surprised, the vibration can be surprised very smoothly and fast. To show the effectiveness of the proposed adaptive control, we compared the results within a high order system. So this is the free vibration of the beam without control. Here is the length of the beam, and in this axis is the time that evolves. You can see the without control, the beam it can be stable there in around 15 seconds. We further did the simulation with PD control. We can see the vibration can be surprised at around 5 seconds. Well, we also tested the control with the proposed method. We can see the vibration can be surprised within around 2 seconds. So this shows the effectiveness of the proposed method. Here we have the conclusions and the future works. The first is the main contributions of this thesis. First is the development of the PDE-based model and the ODE-based model for the submerged piezoelectric cantilever beam. And then we developed the adaptive parameter estimation strategy for the beam system with one mode. And then we developed the estimation method for multiple mode system by using inputs and outputs. And then we developed the USDE-based vibration control. And Finally, we develop the adaptive control. The future work will be based on the following aspects. First is to design parameter estimation algorithms and controllers on PDE-based systems. And second is to reduce the computation cost of learning-based controller. You may see the adaptive control. We were not able to conduct it in experiments because the sampling time is used is smaller than the device. So if we use, we can design a better performance with compact real the hardware. We can conduct the experiments. The third is to relax persistent excitation condition, which is necessary in parameter estimation. Sometimes it may not be fulfilled. So this work is supported in part by Chinese Scholarship Council, and the program is mainly developed within the Horizon 2020 project. And I will also thank to the National Project of China and the Yunnan Project. So thank you for your attention. So that's my defense for my thesis. Thank you.